Okay, getting right back to it. The intermediate value theorem, here we go. I'll go ahead and read it, and then we'll look at some pictures and try and make sense. This is going to be pretty common in our course and really just math at this level and beyond. When you first read a theorem, it's probably going to sound like incredibly technical and like, what is even happening here? There's way too much going on. But you kind of take some time, do a drawing, and oftentimes you're like, oh, that's what they're trying to say. Yeah, of course, you know. And I think the intermediate value theorem is definitely one of those cases. So let f of x be continuous on the interval a to b, and n be between f of a and f of b. Then there exists c in ab such that f of c equals n. You first read that, you're like, what? Okay, what's happening? First, f of x is continuous on this interval from a to b. So that's an x interval. It doesn't have, when we say continuous, we mean there's no jumps, no holes, no asymptotes anywhere starting from A ending at B. Capital N is between the y values of the starting and ending points. So if we were to locate f of A and we were to locate f of B, N is somewhere between them. And it turns out we could take N to be anywhere between, but let's just take, you know, a specific spot like right here, somewhere between the starting and ending y values. What's the conclusion? Then, if this is all true, then there exists C in AB. So there's a C down here on the x-axis such that f of C is equal to N. So what does that mean? So if N is anywhere between f of A and f of B, then we could draw that line out and locate the point. And if we come down to the x-axis, that x-axis, that point on the x-axis is always going to fall somewhere between A and B. And we can see that right here. If we draw that line out for N, right, there's about where the point is, and then we drop that straight down. What we're saying is when we drop it straight down, you're always going to fall between A and B, somewhere between A and B. And you kind of be like, well, yeah, I mean, wouldn't that have to be true? I mean, if you're between the y values and it's continuous, so it's not like, you know, starting over here and then there's a big jump and it ends up, you know, there's nothing unusual like that. Well, yeah, wouldn't that have to be the case? Okay, well, it doesn't have to be this simple. Let's look at another drawing. In this case, okay, here's A to B, or A and B on the X. Let's make f of A higher than f of B. That could happen, right? F of A could be the higher number. F of B could be down here. And let's even make the function not just go like, you know, straight from one point to the other, but it can go up and down. It can even leave, you know, that range of y values. So it could come up first and then dip down below and then back, so long as it's continuous and it eventually ends up at f of B. What we're saying, we can take N, so long as it's between f of A and f of B, we could take it to be anywhere. There will be x values that produce this N as their y value. In fact, in this case, it's going to happen more than once. If we draw that line out, there it happens one time, right there. It happens again, and it happens again. And each one of those are x values that occur somewhere between A and B. So we know that C is in that interval A to B. Here, we might call them C1, C2, and C3, since it happens 3 times. What the theorem guarantees is that there's at least one value C that would produce N as its y value, but it might happen more than once. There exists at least one time it's going to work. Kind of summarize this theorem in maybe more everyday language. What we're trying to communicate is the function hits every y value between the starting and ending y values. Again, you know, we could take n to be anywhere between a and b, right? And there's always going to be an x value that produces that y value with the x value between a and b. Here, it might happen more than once. Okay, let's take a look at this example. How is this useful? How's this going to come into play? Let's use the intermediate value theorem to show that this equation has a solution in the interval from 1 to 2. Okay, I'm going to write this out. Natural log of x equal to e to the negative x has a solution in the interval from 1 to 2. All right, let me switch cameras. Okay. Now you might think, well, why do we need the intermediate value theorem for this? I mean, couldn't we just solve that equation just, you know, by isolating x? Good luck with that. Just because of the nature of there being a natural log on the left and an e on the right, we're not going to be able to algebraically isolate x. You know, just kind of play around. You know, if I said, well, what if we want to get this x by itself? We should take, you know, put both sides in the power of e. Sure, that would cancel here, but we haven't solved for x because we still have it, you know, on the right side. And if we tried to do the opposite, if we took the natural log of both, you know, sure, these are going to cancel out, but, you know, even if we move the negative, right, there's still an x there. So we can't, turns out we cannot algebraically isolate x. That said, there still is a solution. There's an x value that will make those equal, and they give us a hint that it's somewhere between 1 and 2. Okay, so we're thinking, all right, how is the intermediate value theorem going to translate to this equation? Well, there's our interval from a to b, right? We're off to a good start. We know the interval. The intermediate value theorem also has a function, f of x. How are we going to figure out what that function is? Here's a great way to do it. Take your equation and set one side equal to 0. So here, I think it's simpler. I'm just going to subtract that e from both sides. So I'm going to rewrite this as the natural log of x minus e to the negative x equals 0. This is my function right here. At the same time, this, what it's equal to, will be the capital N. That's what my function is. If we can find an x value that makes this equal to 0, we got it, right? We solved it. Okay, check it out. We're going to take this function and evaluate it at both of our endpoints. We're going to find f of 1 and we're going to find f of 2. Let's see what happens here. F of 1, there's our function, right? So the natural log of 1 minus e to the negative 1. Turns out natural log of 1 is 0. So this is simply negative e to the negative 1. What number is that? I'm going to break out my calculator really quick just to get an idea. This is about negative 0.368. Okay, noted. How about f of 2? Natural log of 2 minus e to the negative 2. Well, can't simplify that any. I'm just going to put it right into my calculator. The natural log of 2 minus e to the negative 2, just to get an approximation. That's about 0.558. Now it turns out these are very good results for us. Like, why? We just plugged in some numbers. Yes, but take a look. One of them is negative. That's less than 0. The other is positive. This is greater than 0. The starting y value was negative. The ending y value was positive. Well, if it began negative and ended positive, didn't it have to pass through 0 at some point? At some point between x equals 1 and x equals 2, the y value was 0. Agree with that? It would have to be, right? Well, that was the end we were looking for, right? So we almost, we showed there's some x value between 1 and 2 that would give us the function value equal to 0. So what we'll say, there exists, a little more formally, there exists C in that interval from 1 to 2 such that f of C equals 0. We don't know where that happens, but we know it does. If that's the case, then the natural log of C minus e to the negative C equals 0, right? That's f of C. Or in other words, the natural log of C is equal to e to the negative C, where C is in 1 to 2. We just showed it. There has to be a C, an x value between 1 and 2 that makes our function equal to 0, or in other words, solves that original equation, the natural log of x equals e to the negative x. So there's not really like, this might be like kind of anticlimactic in a way. Like, it's really interesting once you get it. But really, what are we trying to do? We knew there was a solution. So we weren't trying to find the solution. We're just trying to show beyond any doubt, according to this theorem, that it works. And so because the way we set up our function, and because when we plugged in the endpoints, we got 1 negative and 1 positive, then it must be that at some point between them, it passed through 0, and that's all we needed. And after that, we were just kind of wrapping it up and stating it clearly that there's a value of C in 1, 2, which makes these equal. Let's look at the graph very quickly for our function. What we had, the natural log of x minus e to the negative x. And yep, we can see I'll even put in our starting and ending values. So at 1, right, we were here at about negative 0.368. The ending y value was up here at 0.558 or so, giving it a little bit better accuracy here in Desmos. Well, if it started negative and ended positive, we had no idea what the graph was doing, but we knew at some point it had to go through 0. And here it is at about 1.31 is when it actually happens. That is the solution to our equation. But of course, with intermediate value theorem, we just showed that it had to happen. You would need to produce a graph to actually get an approximation for exactly where it is. But yeah. Now you might ask, hey, did we have to do it, with this style natural log x minus e to the negative x. No, it could have been done the other way. Now we could have taken the function to be this. No problem. I think that ends up reversing what is positive and what is negative, but still we're going to show it. If we get one negative and one positive, doesn't matter the order. We know it passes through 0 at some point between them. There's actually a lot of other kind of interesting applications of the intermediate value theorem. You can prove, think about where you, the location where you, let's say you woke up this morning and where you are right now. You can prove that at some point between the time you woke up and between this moment right now, at some moment, you were exactly the same distance away from both locations. So for me, right, I got up at my house, my bedroom, and I came in and now I'm at my office. Well, I, traveled in my car, drove the freeway and all of that. And I kind of, it wasn't a direct route, right? I went west for a while, and then I went north, and then I went west again, and I went north again, and, kind of did that thing on the freeway. Well, at some moment, as I was traveling, I was exactly the same distance away from where I woke up and where I am right now. And, not on the road, but, just the straight as the crow flies distance. I was perfectly in the center at least one moment, maybe multiple times, depending on my route. So that's kind of cool. There's other kind of interesting consequences of the intermediate value theorem that are fun, but I'll save those for another time. That's it for 2.5. Good work.